Imagine you are standing on the shore of a dark, cosmic ocean. You have a bottle, and inside, a message. You're about to throw it into the water, knowing it will drift silently for billions of years, long after you and everyone you know is gone. This is the quiet, true story of the Voyager probes, humanity's loneliest and most hopeful ambassadors. We sent them to take a quick look at our giant planetary neighbors, a simple postcard tour. But along the way, they would discover fiery volcanoes on a frozen moon, hear the strange singing sound of interstellar space itself, and ultimately, they would turn around to take one last heartbreaking photograph of us, a single pale blue dot. Their journey begins not with a launch, but with a lucky once-in-a-lifetime alignment of the heavens. Before we can talk about the probes themselves, we have to talk about the opportunity that gave them life. In the world of celestial mechanics, timing is everything. And in the late 1960s, a graduate student named Gary Flandreau, working at NASA's Jet Propulsion Laboratory, made a remarkable discovery. He was studying the future orbits of the outer planets, and he found something that only happens once every 176 years. He found that in the late 1970s, the four giant outer planets, Jupiter, Saturn, Uranus, and Neptune, would all be perfectly aligned in a single quadrant of the solar system. This was not just a pretty celestial arrangement, it was a golden opportunity. It meant that a single spacecraft could, with the right trajectory, visit all four of these worlds in a single, continuous journey. This was possible because of a beautiful piece of physics called a gravity assist, or a slingshot maneuver. Let's just quietly appreciate how this works. Imagine you are throwing a small ball past a fast-moving bowling ball. If you aim it just right, the bowling ball's gravity will grab your little ball, whip it around, and then fling it away at a much higher speed. The little ball has, in a sense, stolen a tiny bit of the immense orbital energy of the bowling ball itself. By carefully aiming a spacecraft to fly close behind a massive planet like Jupiter, mission planners can use the planet's gravity to both accelerate the spacecraft and bend its trajectory, flinging it outwards towards the next target. This technique saves an enormous amount of fuel and, more importantly, time. A direct flight to Neptune, for example, would take about 30 years. But by using a series of gravitational slingshots off Jupiter and Saturn, the Voyager probes could make the journey in just over a decade. This rare planetary alignment, a cosmic billiard shot set up by the quiet, patient laws of gravity, created a window for a grand tour of the outer solar system. It was an opportunity that was too good to pass up. NASA initially proposed a massive project with 4 separate probes, but budget cuts in the post-Apollo era scaled the ambition down. The final plan was for 2 identical spacecraft, initially called Mariner 11 and 12, to be sent to Jupiter and Saturn. Any journey beyond that to Uranus and Neptune was considered a bonus, a long shot. These 2 probes were renamed before launch. They were given a more poetic and fitting name for their long, lonely journey, Voyager. And so we come to the machines themselves. The Voyager 1 and 2 probes are masterpieces of 1970s engineering, built to last for decades in the harsh, cold, and radioactive environment of deep space. They are not sleek and aerodynamic because they were never meant to fly through an atmosphere. They are wonderfully practical and utilitarian-looking machines, a strange asymmetrical collection of instruments, antennas, and booms. At the center of each probe is a 10-sided bus-like structure that holds the electronics and computers. Sprouting from this is the most prominent feature, a massive 3.7-meter-wide high-gain antenna, a giant white dish that looks like a satellite TV receiver.
This is the probe's mouth and ears, its connection to home, used to send back its precious data and to receive commands from Earth across billions of kilometers of empty space.
Extending out from the main body are 3 long booms. One boom holds the scientific instruments like the cameras and spectrometers, keeping them away from the main body to avoid interference. A second, even longer boom holds the magnetometers, instruments that measure magnetic fields, placing them as far away as possible from the probe's own electronics. And the third boom is perhaps the most important of all. It holds the probe's power source. How do you power a spacecraft that is designed to travel so far from the sun that solar panels would be useless? The answer is a quiet, reliable, and slightly ominous-sounding technology called a radioisotope thermoelectric generator, or RTG. This is, in essence, a nuclear battery. Inside the RTG are several pellets of the radioactive element plutonium-238. As this plutonium naturally decays, it gets very, very hot. This heat is then converted directly into electricity by a series of devices called thermocouples. The RTG has no moving parts. It is a simple, solid-state device that provides a steady, reliable, and very long-lasting supply of power. It is the quiet, radioactive heartbeat of the Voyager probes. When they were launched, their RTGs provided about 470 watts of power, enough to run a few light bulbs. Today, over 45 years later, as the plutonium has slowly decayed, that power output has dropped to about half of its original value. And it is this slow, inevitable decay that will one day, likely in the next few years, cause the probes to finally go silent forever. And what about the brains of this machine? The computer technology of the Voyager probes is a beautiful and humbling reminder of how far we have come. The central computer on each probe has a total of about 69 kilobytes of memory. Not gigabytes, not megabytes, kilobytes.
That is less memory than you would need to store a single short email on your phone today. The processing power is equally modest, capable of executing only about 81,000 instructions per second. Your modern smartphone is millions of times more powerful. And yet, this ancient, simple digital brain has been flying one of the most complex and successful missions in human history for nearly half a century. How is this possible? The answer lies in brilliant, efficient programming and a robust, redundant design. The software was designed to be incredibly resilient, and the hardware itself has numerous backups. The probes have redundant thrusters, redundant radio receivers, and even redundant computer systems. This quiet, careful, and slightly paranoid engineering philosophy is the key to their incredible longevity. They were built to last. But the Voyager probes were designed to be more than just robotic explorers. They were also designed to be ambassadors. They were to be humanity's first deliberate messengers to the cosmos. And that brings us to the most beautiful and philosophical part of the entire mission. As the Voyager probes were being built, a small team at NASA, led by the brilliant astronomer and science communicator Carl Sagan, was tasked with an incredible and almost impossible challenge: to create a message from humanity, a greeting to any advanced extraterrestrial civilization that might one day, perhaps billions of years from now, encounter one of our silent, drifting probes. What do you say on behalf of an entire planet? How do you summarize all the joy, the pain, the art, the science, and the diversity of the human experience in a single small package? The committee wrestled with these profound questions. They knew that any civilization that could find and retrieve Voyager would be incredibly advanced, so they didn't need to send a simple hello. They wanted to send a portrait of our world. The result was the Golden Record. The Golden Record is a beautiful artifact. It is a 12-inch gold-plated copper phonograph record, protected by an aluminum cover. Gold was chosen because it is a very inert material. It will not tarnish or degrade in the vacuum of space for billions of years. Etched onto the cover of the record is a set of simple, elegant diagrams designed to be a kind of instruction manual. The diagrams show the location of our solar system relative to 14 known pulsars, using their unique pulse periods as a kind of cosmic address. This is the famous pulsar map. It also includes a diagram showing how to play the record. It indicates the correct rotational speed and shows a diagram of the stylus and cartridge that are included with the record, so that an alien civilization could, in theory, build a record player to listen to our message. And finally, there is a diagram depicting the two lowest energy states of the hydrogen atom, the most common element in the universe. This is meant to be a universal clock, a way of communicating a fundamental unit of time. And what is on the record itself? What did we choose to say to the cosmos? The contents are a beautiful and sometimes quirky mix of sounds, music, and images, a true mixtape from planet Earth. The first sounds on the record are a collection of greetings in 55 different languages, both ancient and modern. It begins with a greeting in Akkadian, a language spoken in ancient Sumer about 6,000 years ago, and it moves through languages like Latin, Mandarin Chinese, and Welsh before ending with a modern Chinese dialect. The English greeting, spoken by a child, simply says, "Hello, from the children of planet Earth." It's a quiet, hopeful, and deeply touching opening. After the spoken greetings, the record contains a section called The Sounds of Earth. This is an incredible 12-minute-long audio collage designed to give a brief, impressionistic sense of our planet and its inhabitants. It is a quiet symphony of our world. The sounds begin with the planet itself. We hear the sound of volcanic eruptions, earthquakes, and thunder, the powerful geological sounds of a living world. Then we hear the sound of wind and rain, the gentle, life-giving sounds of our weather. From there, we move to the sounds of life. We hear the chirping of crickets and frogs, the songs of birds, the barking of dogs, and the incredible, haunting songs of humpback whales. We hear a chimpanzee. And then we hear ourselves. The recording includes the sound of a human heartbeat, a sound that is both deeply personal and universally shared. We hear the sound of laughter, a beautiful, unfiltered expression of human joy. We hear the sound of a mother comforting her crying child and the sound of her kiss. The collage then moves on to the sounds of our technology. We hear the rhythmic clatter of a train, the roar of a tractor, the clanging of a blacksmith's hammer, and the whine of a saw cutting through wood. And finally, we hear the sounds of our own exploration, the powerful roar of a Saturn V rocket lifting off, a quiet testament to the very journey that this record is embarking on. It is an incredible, poignant, and deeply moving audio portrait of our world, a quiet and beautiful message sent out into the great silence. Following the sounds of Earth, the Golden Record contains a long section of music, a 90-minute playlist designed to showcase the breadth and diversity of human culture. The selection process was a huge undertaking, with the committee trying to choose pieces that were both representative of different cultures and also, in some way, universally beautiful. The musical journey is an eclectic and wonderful one. It begins with the classical music of the West. There are 3 separate pieces by Johann Sebastian Bach, who Carl Sagan reportedly felt was the perfect musical ambassador for humanity. There is Mozart, and there is Beethoven's famous Fifth Symphony. But the musical selection goes far beyond just European classical music. It is a true world music collection. There is traditional panpipe music from Peru, initiation songs from New Guinea, and ancient zither music from China. There's a beautiful piece of Aboriginal music from Australia, played on the didgeridoo. There is folk music from Bulgaria and jazz from Louis Armstrong. And then there is Chuck Berry. When the committee was deciding what piece of rock and roll music to include, they chose his iconic song, Johnny B. Good. It's a wonderful choice, a vibrant, joyful, and quintessentially American piece of music. There's a famous, slightly ironic joke from the TV show Saturday Night Live about this. The joke goes that if an alien civilization ever found the record, their message back to us would simply be, "Send more Chuck Berry." It's a quiet, funny thought, the idea of aliens billions of years from now discovering the joy of 1950s rock and roll.
The final section of the Golden Record is a collection of 115 images. These were encoded onto the record in an analog audio format. An advanced civilization would, in theory, be able to decode these audio signals back into images. The images were chosen to be a visual encyclopedia of our world and our species. The sequence begins with the basics. There are diagrams of our solar system, our planet, and our chemical makeup. There is a detailed anatomical drawing of a human man and woman, showing our external and internal biology. Then, there are images of human life and culture. We see pictures of people from all over the world eating, drinking, and playing. There's a beautiful picture of a group of children of different ethnicities. There's an image of an astronaut on a spacewalk. There's a picture of a grocery store showing the abundance of our food. There is a picture of a traffic jam, a quiet, honest admission of our frustrations. There is even an X-ray of a human hand. And finally, there is a printed message from the US President at the time, Jimmy Carter. His message is a quiet, hopeful, and beautiful one. It reads, in part, "This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours. We hope someday, having solved the problems we face, to join a community of galactic civilizations. This record represents our hope and our determination, and our goodwill in a vast and awesome universe." With this message complete, the golden records were mounted to the sides of the two Voyager probes, protected by their aluminum covers, ready for their endless journey. They are a quiet, profound testament to the optimistic spirit of the age in which they were built.
And so, in the late summer of 1977, the two Voyager probes, with their golden records attached, were ready for their launch. In a strange quirk of mission planning, Voyager 2 actually launched first on August 20th. Voyager 1 launched a couple of weeks later, on September 5th, but it was on a faster, shorter trajectory, so it would arrive at Jupiter and Saturn first. The grand tour had begun. For the next year and a half, the probes journeyed through the inner solar system and the asteroid belt, their instruments quietly observing the solar wind and the space environment. Then, in early 1979, Voyager 1 made its approach to our first great destination on this tour, the planet Jupiter. The encounter with Jupiter was a revelation. We had sent two smaller Pioneer probes past Jupiter before, but the images and data from Voyager were on a completely different level. For the first time, we saw Jupiter not as a distant fuzzy disk, but as a dynamic, churning, and incredibly complex world. The close-up images of its atmosphere were mesmerizing. They showed the famous cloud bands to be incredibly turbulent, with giant storms and eddies swirling at their boundaries. And of course, Voyager gave us our first detailed, intimate look at the Great Red Spot. We saw that it was not a placid red cloud, but a colossal, raging anticyclonic storm, a hurricane wider than our entire planet, with winds of over 400 kilometers per hour. We could see smaller storms being swept up by it, circling it for a few days before being completely consumed. It was a storm of almost unimaginable power and longevity. Voyager also gave us our first discovery of something we never expected Jupiter to have, a faint, dark, and dusty ring system, something that is completely invisible from Earth.
But the single greatest discovery of the entire Jupiter encounter, a discovery that completely revolutionized our understanding of the solar system, came not from the planet itself, but from its innermost large moon, Io. Before Voyager, we expected the moons of the outer solar system to be quiet, cold, dead, cratered worlds, much like our own moon. But when Voyager 1 sent back its first close-up images of Io, the scientists at JPL were baffled. The surface was not gray and cratered. It was a bizarre, psychedelic canvas of yellow, red, orange, and black. And there were no impact craters at all. The surface was incredibly young. What could possibly be erasing the craters and painting the surface with these strange colors? The answer came from a navigation engineer named Linda Morabito. While analyzing one of the images of Io's limb, she saw something strange, a faint, plume-like cloud erupting from the surface and rising high into space. At first, she thought it was a problem with the image, but she checked other images, and it was there. She had discovered the first active volcano ever seen on another world. It turned out that Io is the most volcanically active body in the entire solar system. It is covered in hundreds of volcanoes that are constantly erupting, spewing out massive plumes of sulfur and sulfur dioxide. This is what gives the moon its strange, pizza-like colors. The constant volcanic activity is constantly repaving the surface, burying any impact craters. The reason for this intense volcanism is the immense gravity of Jupiter, which constantly squeezes and flexes the little moon, heating its interior through tidal friction. The discovery of active volcanism on Io was a quiet, stunning revelation that the outer solar system was not a dead, frozen place, but was dynamic, active, and full of surprises.
After its triumphant encounter with Jupiter, Voyager 1 used the planet's immense gravity to slingshot itself onwards, towards our next destination. In November of 1980, it arrived at the beautiful ringed planet Saturn. Once again, the images Voyager sent back were breathtaking and filled with new discoveries. The mission gave us our first truly close-up, high-resolution views of Saturn's magnificent ring system. And it revealed that the rings were far more complex and far stranger than we had ever imagined. From Earth, the rings looked like a few simple, solid bands. But Voyager's images showed that they were actually composed of thousands upon thousands of individual narrow ringlets, like the grooves on a phonograph record. The images also revealed strange, dark, radial features in the B ring, the widest and brightest of the rings. These features, which looked like the spokes on a bicycle wheel, would form and then dissipate in a matter of hours. They seemed to rotate with the planet as if they were solid, defying the laws of orbital mechanics. These spokes were a complete mystery. The leading theory today is that they are clouds of tiny electrostatically charged dust particles being levitated above the main ring plane by Saturn's magnetic field. Voyager also discovered several new, small moons orbiting within and near the rings. It showed us the strange shepherd moons, like Prometheus and Pandora, that orbit just inside and outside of the F ring, and whose gravity helps to keep the narrow ring sharply defined. And it gave us our first detailed look at Saturn's largest and most mysterious moon, Titan. Voyager's cameras could not see through Titan's thick, hazy orange atmosphere, but its instruments confirmed that the atmosphere was incredibly dense, even denser than Earth's, and that it was made mostly of nitrogen, just like our own. It was a tantalizing glimpse of a strange, Earth-like,
but deeply alien world.
After its successful encounter with Saturn, Voyager 1's grand tour came to an end. Its trajectory, which had been designed to give it a close look at Titan, sent it flying up and out of the plane of the solar system on a path that would not take it to any other planets. Its primary mission was over. Now its long, quiet journey to the stars would begin. But its twin, Voyager 2, was on a slightly different path. After its own successful flyby of Saturn in August of 1981, it was in a perfect position to use Saturn's gravity to perform another slingshot maneuver, this time sending it on a 4.5-year journey to the next great unexplored world, the planet Uranus. In January of 1986, Voyager 2 arrived at its destination. It remains, to this day, the only spacecraft to have ever visited this distant, strange, and quiet ice giant. The images it sent back were, at first, a little underwhelming. Unlike the turbulent, colorful clouds of Jupiter and Saturn, Uranus appeared as a nearly featureless, pale cyan blue ball. It was a serene, almost placid-looking world. But the science it performed was revolutionary. It confirmed the planet's bizarre, extreme axial tilt. Uranus is literally on its side, its poles pointing where most planets have their equators. Voyager 2 also discovered 11 new moons orbiting the planet, and it gave us our first detailed look at its faint, dark ring system. The rings of Uranus are not like Saturn's bright, icy rings. They are made of incredibly dark material, as black as charcoal, which makes them almost invisible. And finally, Voyager 2 discovered that Uranus has a very strange and lopsided magnetic field, which is tilted by nearly 60 degrees from its rotational axis and is not centered on the planet's core. The most fascinating part of the Uranus encounter, however, was the flyby of its innermost major moon, Miranda. Miranda is a small, icy moon, only about 500 kilometers in diameter. But its surface is one of the most bizarre and chaotic landscapes in the entire solar system. It looks as if it has been smashed to pieces and then haphazardly glued back together. The surface is a jumble of completely different types of terrain, all pushed up against each other. There are old, heavily cratered regions right next to young, smooth plains. There are vast, deep canyons, some of them 10 times deeper than the Grand Canyon on Earth. And most strangely, there are 3 huge, roughly rectangular or oval-shaped features called coronae. These are vast, grooved structures that look a bit like giant racetracks. What could have possibly created such a Frankenstein-like world? The leading theory is that Miranda was, at some point in its distant past, completely shattered by a massive impact. The fragments would have remained in orbit, and then, over time, gravity would have slowly pulled them back together, but in a messy, random, jumbled configuration. Another theory is that the strange features are the result of large upwellings of partially melted ice from the moon's interior. Whatever the cause, Miranda is a quiet, beautiful puzzle, a tiny world with a remarkably violent and complex history. After its brief but revealing encounter with the Uranian system, Voyager 2 performed one last perfect gravity assist. It used Uranus's gravity to fling it on the final leg of its grand tour, a 3.5-year journey to the final, unexplored planet in our solar system, the deep blue world of Neptune. In August of 1989, 12 years after it had left Earth, Voyager 2 arrived at the 8th planet from the Sun, Neptune. This was the final planetary encounter of its long mission, and it was a spectacular one. Neptune, unlike the placid-looking Uranus, was a vibrant, deep blue world, racked by powerful storms. The most prominent of these was a massive, swirling dark blue storm system that was nicknamed the Great Dark Spot. It was a huge anticyclone, about the size of the Earth, very similar in nature to Jupiter's Great Red Spot. Voyager 2 also clocked the winds on Neptune and found them to be the fastest in the entire solar system. Supersonic winds, driven by the planet's small internal heat source, whip through its upper atmosphere at speeds of over 2,000 kilometers per hour. Voyager 2 also discovered Neptune's own faint, dark, and clumpy ring system. Unlike Saturn's uniform rings, Neptune's rings have bright, dense arcs where the material is much thicker, a feature that is still not fully understood. But once again, the greatest discoveries came from one of the planet's moons. Voyager 2 performed a close flyby of Neptune's largest moon, Triton. And Triton turned out to be one of the strangest and most fascinating worlds in our solar system. First, it has a retrograde orbit, meaning it orbits Neptune backwards. This is a dead giveaway that it is a captured object, a dwarf planet from the Kuiper Belt that was snared by Neptune's gravity long ago. And despite being one of the coldest objects in the solar system, with a surface temperature of -235 degrees Celsius, Triton is geologically active. Voyager 2's images showed a young, varied surface, and most remarkably, it saw dark plumes erupting from the moon's south polar region. These were cryovolcanoes, or ice volcanoes, spewing nitrogen gas and dark, entrained dust several kilometers up into Triton's thin nitrogen atmosphere. The discovery of active geysers on this distant, frozen world was another stunning revelation, a perfect final surprise at the end of the grand tour.
With its triumphant flyby of Neptune and Triton, Voyager 2's planetary mission was complete. It had successfully visited all 4 of the outer giant planets, a feat that will not be repeated for many generations. Both Voyager 1 and Voyager 2 were now on escape trajectories, their speed great enough to overcome the sun's gravity. Their new, final mission had begun, a quiet, endless journey into the interstellar void. But before they left the neighborhood entirely, the Voyager 1 probe, at the persistent and passionate request of Carl Sagan, was tasked with one final, poignant act of observation. This brings us to a quiet, famous moment in our history. In February of 1990, when Voyager 1 was about 6 billion kilometers from home, far beyond the orbit of Neptune, NASA engineers sent the commands to turn the spacecraft's camera around and take one last look back at the solar system it was leaving behind. It took a series of 60 images, a family portrait of our solar system from the outside. Most of the planets were just small points of light, but one image in particular became an icon. In it, the Earth is captured as a single, tiny, almost invisible pixel of light suspended in a scattered ray of sunlight. This is the famous pale blue dot photograph. It is a deeply humbling and profoundly moving image. All of human history, every person you have ever known, every joy and every sorrow, every king and every peasant, every creator and destroyer of civilization, all of it is contained within that single, tiny mote of dust, suspended in a sunbeam. It is a quiet, powerful lesson in perspective. Carl Sagan himself wrote about it with incredible eloquence, and his words are worth quietly reflecting on.
He saw it as a powerful lesson in perspective, a way to show the world the true scale of our existence. He campaigned for years to get NASA to agree. The engineers were hesitant. Pointing the camera so close to the bright sun risked permanently damaging its sensitive optics. But Sagan persisted. And finally, on February 14th, 1990, they agreed. They turned Voyager 1 around and took the picture. The image that came back is not spectacular in a traditional sense. It is a grainy, simple photograph, but its emotional and philosophical power is immense. It shows the Earth as a single, tiny, almost invisible pixel of light, less than a single pixel wide. It is a mote of dust, caught in a scattered ray of sunlight in a vast and empty cosmic arena.
Carl Sagan's own reflection on this image has become one of the most beautiful and profound pieces of writing about our place in the universe. So let's just quietly listen to a part of what he said. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. His words are a quiet, powerful meditation on humility and the importance of kindness. He concluded that, to him, the image underscored our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
The taking of the pale blue dot photograph was, in many ways, the end of Voyager's role as an imaging spacecraft. After that final, poignant look back, the cameras were powered down forever to save precious energy for the long journey ahead. The probes would now become explorers of a different kind, using their other instruments to taste and feel the environment around them. Their next great task was to become humanity's first emissaries to the space between the stars. To understand this next chapter of their journey, we have to understand the environment they were traveling through. Our solar system is not just a collection of planets sitting in empty space. The sun creates a huge protective bubble around itself. This bubble is called the heliosphere. It is a vast region of space, extending far beyond the orbit of Pluto, that is inflated by the constant outward pressure of the solar wind. Inside this bubble, we are protected. The heliosphere acts as a shield, deflecting the majority of the high-energy galactic cosmic rays that are streaming in from the wider galaxy. It is our solar system's own quiet, invisible force field. But this bubble is not infinite. At some point, very far from the sun, the outward push of the solar wind must meet the inward pressure of the interstellar medium, the thin gas and dust that fills the space between the stars. The boundary where this happens is called the heliopause, and it is the true physical edge of our solar system. The journey of the Voyager probes through the outer layers of this bubble is a story in itself. The first major boundary they had to cross was the termination shock. This is the point where the solar wind, which has been expanding outwards at supersonic speeds, suddenly and dramatically slows down as it begins to interact with the interstellar medium. It is a colossal, invisible shockwave at the edge of our solar system. In December of 2004, Voyager 1, then about 14 billion kilometers from home, finally crossed this boundary.
The crossing of the termination shock was a major milestone, and it was full of surprises. Scientists had theories about where it should be and what it would be like, but Voyager's direct measurements gave us our first real data. The location of the shock was much closer than some models had predicted, telling us that our heliosphere is perhaps being compressed by the interstellar magnetic field more than we thought. After crossing the termination shock, Voyager 1 entered a strange, new, and completely unexplored region of space. This is the heliosheath. This is the turbulent, frothy outer layer of our heliosphere. It's the region where the slowed-down, hot solar wind is deflected and flows along the boundary with interstellar space, much like the water of a river flows around a large boulder. This region is a chaotic, messy, and turbulent place. The magnetic field from our sun becomes tangled and foamy.
Voyager 1 spent nearly 8 years traveling through this strange, frothy boundary layer. And then, in August of 2012, something remarkable happened. The spacecraft's instruments detected a sudden, dramatic, and permanent change in its environment. The level of high-energy galactic cosmic rays from outside the solar system suddenly jumped up dramatically. At the same time, the level of lower-energy particles from within our solar system dropped to almost zero. The data was clear. After a 35-year journey from Earth, Voyager 1 had finally punched through the heliopause. It had officially crossed the boundary and entered interstellar space. It was the first human-made object to ever do so. This was a monumental achievement, but it raised a new question. How could we be sure? The magnetic field data was a bit ambiguous, but then a lucky break from the sun allowed for a definitive confirmation. A large solar flare from our sun a few months later sent a wave of plasma traveling out through the solar system. When this wave eventually reached Voyager 1, many months later, it caused the interstellar gas around the probe to vibrate or ring like a bell. This brings us to one of the most beautiful and strange discoveries of the entire mission: the sound of interstellar space. Voyager's plasma wave instrument was able to detect the vibrations of the interstellar gas as this solar shock wave passed by. These vibrations are a direct measure of the density of the plasma, and the frequency of these vibrations is actually within the range of human hearing. So scientists were able to convert this plasma density data directly into an audio signal. And for the first time, we could hear the sound of the space between the stars. It is not a dramatic roar or a simple hiss. It is a quiet, gentle, and slightly eerie rising tone, a pure, high-pitched whistle that sounds almost like a strange kind of music. It is the sound of the thin, tenuous plasma of the interstellar medium, vibrating in response to a shock wave from our own distant sun. The density of the plasma was exactly what was predicted for interstellar space, confirming without a doubt that Voyager 1 was truly outside. A few years later, in 2018, its twin, Voyager 2, also crossed the heliopause and entered interstellar space. Because Voyager 2 was on a different trajectory, it crossed at a different location. And its data, combined with Voyager 1's, has given us a much more complete picture of the shape of our heliosphere. It seems our solar system's protective bubble is not a perfect sphere. It is likely a bit squashed and asymmetrical, shaped by its journey through the local interstellar magnetic field. These two tiny, ancient probes are now our only direct observers of the environment beyond our home. They are our silent sentinels in the interstellar void, still, after all these years, sending back quiet whispers about the nature of the great cosmic ocean in which our small, sunny island is floating. Now let's take a quiet journey back in time, back to the 1970s, and revisit that incredible message we sent out with these probes. Let's take a deeper, more contemplative look at the Golden Record. The creation of this record was a project of immense hope and profound intellectual humility. The team, led by Carl Sagan, knew that the chances of the record ever being found by another civilization were infinitesimally small. The probes will not come close to another star for tens of thousands of years. The record was not really a message sent with the expectation of a reply. It was, instead, a symbolic act. It was a testament to our own curiosity, our own hopefulness, and our desire to leave a quiet, lasting legacy of our existence. The committee that was formed to decide on the contents of the record included not just scientists like Sagan and Frank Drake, but also artists, writers, and musicians like the writer Anne Druyan, who would later marry Sagan. They had to make incredibly difficult decisions. How do you represent all of humanity, with all its diversity, its contradictions, its beauty, and its flaws, on a single, small record? They debated every single choice with incredible care. For example, what images of humanity should they include? They decided to include scientific diagrams of our anatomy and our DNA, but they also wanted to show our humanity. There was a debate about whether to include any images of human nudity. Sagan was in favor of it, arguing that it was a fundamental part of our biology. He and artist Linda Saltzman Sagan created a plaque for the earlier Pioneer probes that famously included a simple, line-drawn image of a nude man and woman. But NASA, worried about public controversy, vetoed the idea for the golden record. So the anatomical diagrams are clinical and chaste. It's a quiet, interesting footnote about the cultural sensitivities of the time. Let's now quietly explore the Sounds of Earth section of the record in more detail. This 12-minute audio collage is a masterpiece of sound design, a journey through the acoustic landscape of our planet. It was curated by Anne Druyan. The sequence begins with the sounds of the non-human world. It starts with the music of the cosmos itself, the strange rhythmic sounds of pulsars, and then transitions to the sounds of our own planet's geology, volcanoes, earthquakes, and the rumble of thunder. Then we hear the sounds of our biosphere, the gentle lapping of waves, the howl of wind, the chirping of crickets, the croaking of frogs, and the beautiful, complex songs of birds and whales. Then, the focus shifts to humanity. The first human sound is not a word, but a heartbeat. A recording of Anne Druyan's own heartbeat was included, a quiet, intimate, and universal symbol of life. This is followed by the sound of human footsteps, and then the sound of laughter. After that comes the technology, the sounds of a blacksmith's hammer, a saw cutting wood, a tractor, and a train. The sequence ends with the powerful, roaring sound of a Saturn V rocket launch, the very technology that made the record's own journey possible. And then a quiet, final sound, the sound of a mother kissing her child. It is a beautiful, thoughtful, and deeply moving audio poem about our world. The section of greetings in 55 languages is also fascinating. The team tried to include as wide a variety of languages as possible, from ancient languages like Sumerian and Hittite to modern languages from all over the globe. The English greeting, spoken by the young son of one of the team members, is simple and beautiful. Hello from the children of planet Earth. Each greeting is a quiet, hopeful hello sent out into the vast, silent ocean of space. Now, let's think more about the music. The 90 minutes of music on the Golden Record is an incredible and eclectic mixtape, a journey through the musical traditions of our entire planet. Carl Sagan and his team wanted to showcase the diversity of human culture, but also to choose pieces that had a kind of timeless, universal beauty. The selection of Western classical music is profound. It includes 3 separate pieces by Johann Sebastian Bach. Sagan often said that if you were to send a single composer to represent the intellectual and emotional depth of humanity, it would be Bach. The record includes a piece for violin, a Brandenburg concerto, and the beautiful Gavotte and Rondeau. There is also Mozart's Queen of the Night aria from the Magic Flute, and the first movement of Beethoven's famous Fifth Symphony. But the collection goes far, far beyond just Western classical music. It is a true world music anthology. There is a hauntingly beautiful piece of panpipe music from Peru. There are initiation songs from New Guinea and Zaire. There is a quiet, beautiful piece of music played on an ancient Chinese instrument called the chin. There is vibrant percussion music from Senegal and a beautiful folk song from Bulgaria. There is even early American jazz with Louis Armstrong's Melancholy Blues. And then there is the representative of rock and roll. The committee chose Chuck Berry's iconic 1958 song, Johnny B. Good. Why this song? Because it is a story. It's a story of a poor country boy who could play the guitar just like a ring in a bell. A story of hope, energy, and the birth of a new kind of music. It's a joyful and quintessentially human piece of art. The quiet, funny thought that some alien civilization billions of years from now might discover this record and be introduced to humanity through the sound of Chuck Berry's guitar is a wonderful one. Finally, let's explore the 115 images that are encoded on the record. These images are a visual encyclopedia of our world, a scrapbook of our life and our science, designed to be decoded by an advanced civilization. The sequence begins with the basics, a kind of cosmic address book. There are diagrams of our solar system showing which planet the signal is from. There are diagrams defining our units of measurement. Then there is a detailed section on our science. There are diagrams of our DNA, our chemical composition, and our anatomy. There are pictures of cell division and a beautiful image showing fertilization. Then, the images move on to show the human experience. There is a stunning collection of photographs of people from all over the world, of all ages and all cultures. There is a picture of a group of children of different ethnicities looking at a globe. There is a picture of a father and daughter in Malaysia. There is a picture of a woman in a grocery store surrounded by the abundance of our food. There is a picture of an Olympic sprinter and another of the Golden Gate Bridge. There is even a picture of a traffic jam in India, a quiet, honest admission of our daily frustrations. And there are images of our own exploration. There is a picture of the Arecibo radio telescope. There is a picture of an astronaut on a spacewalk. And there is a picture of a woman with a microscope. The images were chosen to tell a story of a curious, diverse, and technologically developing species living on a beautiful blue planet. The final image in the sequence is a photograph of a string quartet with the musical score for a piece by Beethoven. It is a final, quiet message that connects our science, our art, and our humanity. The Golden Record is a profound and deeply optimistic artifact. It is a quiet, hopeful whisper sent out into the void, carrying the best of who we are. So, with their golden records attached, the two Voyager probes began their long journey. Let's return to their planetary encounters and explore them with a little more quiet detail. We'll start with Jupiter. We know the discovery of the active volcanoes on Io was a complete shock, but let's appreciate why it was so shocking. Before Voyager, our understanding of how worlds were heated was simple. A world could be heated by the sun, or it could be heated by its own internal primordial heat left over from its formation, or by the decay of radioactive elements in its core. Io is a small moon, far from the sun. It should have been completely cold and geologically dead like our own moon. The discovery of tidal heating was a paradigm shift. The idea that a moon could be constantly heated by the gravitational push and pull of its parent planet was a new and revolutionary concept. Io orbits Jupiter in a slightly elliptical path, and it's also in an orbital resonance with the other Galilean moons, Europa and Ganymede. This means their gravity constantly tugs on Io, keeping its orbit from becoming perfectly circular. So as Io orbits Jupiter, it is constantly moving slightly closer and then slightly farther away. This causes the immense gravitational pull from Jupiter to stretch and squeeze the little moon by as much as 100 meters on every orbit. Imagine taking a solid object and flexing it back and forth by 100 meters every 42 hours. This constant flexing generates an incredible amount of internal friction and heat, enough to keep its interior molten and to power its hundreds of active volcanoes. It is a world that is being perpetually tortured by gravity, and the result is a beautiful, violent, and completely unexpected volcanic wonderland.
And what about Europa? We know that this same tidal heating is what likely maintains its hidden liquid water ocean. But Voyager's images gave us our first clues. When scientists looked at the close-up images of Europa's icy surface, they were struck by how smooth and young it looked. There were very few impact craters. This was a huge hint that the surface was being constantly renewed or repaved from below, much like the surface of Io. And the surface was covered in a bizarre, complex network of long, linear cracks and ridges. It looked almost like someone had taken a brown marker and drawn all over a white billiard ball. Scientists now believe that these are fractures in the ice shell, caused by the constant tidal stress. The reddish-brown material in the cracks is likely a salty, mineral-rich brine that has welled up from the ocean below and has been exposed to Jupiter's intense radiation, which darkens and colors it. The most exciting features Voyager saw were the regions of chaos terrain. These are areas where the ice shell appears to have been broken up into large, iceberg-like rafts, which have then drifted apart and refrozen in new, jumbled positions. This is incredibly strong evidence that the ice shell is not frozen solid to the core, but is floating on a layer of liquid or at least slushy, partially melted ice, the great subsurface ocean. The Voyager images of Europa transformed it from a simple, dead, icy moon into one of the most compelling and exciting places in the entire solar system to search for life. It was a quiet, icy world that was suddenly full of incredible promise.
After its triumphant and surprising encounter with Jupiter and its moons, Voyager 1 used the planet's immense gravity to slingshot itself onwards towards our next great destination on this grand tour. In November of 1980, after a journey of nearly 2 years from Jupiter, it arrived at the beautiful, serene, and famously ringed planet, Saturn. Once again, the images Voyager sent back across more than 1 billion kilometers of space were breathtaking and filled with new, quiet discoveries. The mission gave us our first truly close-up, high-resolution views of Saturn's magnificent ring system. And it revealed that the rings were far more complex, more delicate, and far stranger than we had ever imagined from Earth. From our telescopes on the ground, the rings look like a few simple, solid bands, separated by a couple of dark gaps. They look like the single solid groove on a vinyl record. But Voyager's images showed that they were actually composed of thousands upon thousands of individual narrow ringlets, each one orbiting Saturn independently. The level of intricate detail was stunning. The rings were not a solid object, but a vast, shimmering sea of countless individual particles. And the composition of these particles was confirmed to be almost pure water ice. They ranged in size from tiny dust grains to small ice cubes, all the way up to chunks as large as a house or a car. This immense flat river of ice is, as we've discussed, almost impossibly thin. It is a structure of incredible scale and equally incredible delicacy. But Voyager also discovered strange features within the rings that defied our simple models. The most famous of these were the spokes.
These spokes were strange, dark radial features that appeared in the B ring, which is the widest and brightest of Saturn's main rings. They looked like the ghostly shadows of the spokes on a giant bicycle wheel, stretching for thousands of kilometers across the rings. And they were transient. Voyager's cameras watched as they formed and then dissipated in a matter of hours. Their most bizarre property was that they seemed to rotate around the planet as if they were solid, defying the normal laws of orbital mechanics, where the inner parts of the rings should orbit faster than the outer parts. The spokes were a complete and total mystery. The leading theory today is that they are not a gravitational phenomenon, but an electromagnetic one. The idea is that tiny microscopic dust particles in the rings can become electrostatically charged, perhaps by lightning in Saturn's atmosphere. This charge would then cause the dust particles to be levitated slightly above the main ring plane by Saturn's powerful magnetic field. What we see as a dark spoke is actually a cloud of this levitating dust, which then rotates in sync with the planet's magnetic field, not its gravitational field. It's a beautiful and strange idea of magnetic dust storms in a sea of ice. Voyager also gave us a close-up look at the F ring, a very narrow, faint ring that lies just outside the main system. And here, it found even more strangeness. The F ring wasn't a simple, clean circle. It was braided, with multiple strands of material that seemed to be woven together in a complex pattern. And its structure was being actively shaped by two tiny moons, one orbiting just inside the ring and one just outside. These are the shepherd moons, Prometheus and Pandora. Their gentle, persistent gravity is what herds the particles of the F ring into its narrow, strange, and beautiful shape.
Beyond the rings, Voyager 1 performed a close flyby of Saturn's largest and most mysterious moon, Titan. This was a primary goal of the mission. Titan is a unique and fascinating world. It is the second largest moon in our entire solar system, larger than the planet Mercury. And what makes it truly special is that it is the only moon known to have a thick, substantial atmosphere. Before Voyager, we knew Titan had an atmosphere, but we had no idea what it was like. From Earth, all we could see was a hazy orange, featureless ball. One of the great hopes of the Voyager mission was that its cameras might be able to peer through this haze and see the surface below. Was there a solid surface? Were there oceans? No one knew. In November of 1980, Voyager 1 flew past Titan, but the haze was even thicker and more opaque than anyone had expected. The cameras could see nothing of the surface at all. It was a uniform, pumpkin-colored, smoggy sphere. This was, at the time, a little disappointing. But the data that Voyager's other instruments collected about the atmosphere itself was a scientific goldmine. Voyager's instruments confirmed that Titan's atmosphere was even denser than Earth's, with a surface pressure about 50% higher than ours. And it confirmed that the atmosphere was made almost entirely of nitrogen, just like Earth's. This was a stunning discovery. A moon with a thick, nitrogen-rich atmosphere was a completely unexpected find. But mixed in with the nitrogen was a small amount of methane, and it was this methane that was responsible for the thick orange smog. High up in Titan's atmosphere, the sun's ultraviolet light was breaking down the methane molecules and recombining them into a complex soup of organic chemicals, creating the thick haze that hides the surface. This discovery of a thick, nitrogen-rich atmosphere filled with complex organic chemistry was incredibly exciting for scientists who studied the origin of life. They realized that Titan was, in a way, a frozen, preserved snapshot of what the very early Earth might have been like before life arose and filled our own atmosphere with oxygen. It was a natural, planetary-scale laboratory for studying the kind of prebiotic chemistry that might have led to life on our own world. The data from Voyager also led to another tantalizing theory. The conditions on Titan, with its incredible cold and high pressure,
were just right for methane to exist not just as a gas, but as a liquid. This led Carl Sagan and others to famously speculate that Titan's surface, hidden beneath the smog, might be covered in vast oceans not of water, but of liquid ethane and methane. It was a quiet, profound, and for decades unproven idea. It wouldn't be until the arrival of the Cassini-Huygens mission, almost 25 years later, that we would finally see beneath the clouds and confirm that Titan was indeed a world of methane lakes and rivers. But it was Voyager that gave us the first crucial clues. Now, after its close flyby of Titan, Voyager 1's grand tour came to an end. This close encounter with Saturn's largest moon put the spacecraft on a trajectory that sent it flying up and out of the plane of the solar system, on a path that would not take it to any other planets. Its primary mission of planetary exploration was over. Now, its long, quiet, and lonely journey to the stars would begin. But its twin, Voyager 2, was still on its way, and it was on a different path, a path that would take it to the great, unexplored worlds of the deep outer solar system.
Let's now turn our attention back to Saturn's other moons. While Titan is the giant, Voyager 2's encounter revealed a diverse and beautiful family of smaller icy worlds, each with its own unique personality. There is the strange two-faced moon Iapetus. As Voyager 2 approached, it saw that this moon was a world of perfect contrast. One entire hemisphere of the moon, the side that faces forward in its orbit, is incredibly dark, as black as asphalt. The other hemisphere is as bright and white as fresh snow. This yin-yang appearance is one of the most striking visual features in the solar system. As we've discussed, the leading theory is that the leading hemisphere has been slowly coated over billions of years by a thin layer of dark reddish dust from another, more distant moon, Phoebe. It is a quiet, slow-motion paint job on a planetary scale. Then there's the moon Mimas, which became famous for its uncanny resemblance to the Death Star from the Star Wars movies. This is because its surface is dominated by a single colossal impact crater named the Herschel crater. This crater is about a third of the entire diameter of the moon, and it has a large central peak, making it look exactly like the super laser dish of the fictional battle station. The impact that created this crater must have been so powerful that it came very close to completely shattering the little moon to pieces. The evidence of this near catastrophe is visible on the opposite side of the moon, which is covered in fractures and cracks from the shockwave. And then there is our old friend Enceladus. At the time of the Voyager flyby, Enceladus was seen as just another small, bright, icy moon. The images showed a surprisingly smooth surface in some areas, hinting at recent geological activity, but there was no clue as to the incredible secret it was hiding. It would be decades before the Cassini mission would discover the magnificent water plumes erupting from its south pole. But Voyager gave us our first quiet hints that this little moon was something special. After its own successful encounter with the Saturnian system in August of 1981, Voyager 2 was now truly on a journey into the unknown. It performed one last perfect gravity assist, using Saturn's gravity to fling it on a long, quiet 4.5-year journey to the next great unexplored world, the planet Uranus. In January of 1986, after traveling for almost a decade, Voyager 2 arrived at its destination. It remains, to this day, the only spacecraft to have ever visited this distant, strange, and quiet ice giant. The encounter was a brief one, a fast flyby, but the data it sent back completely revolutionized our understanding of this pale blue world. The images it sent back were, at first, a little bit of a letdown after the vibrant chaos of Jupiter and the majestic beauty of Saturn. Uranus appeared as a nearly featureless, pale cyan blue ball. It lacked the distinct cloud bands and giant storms of the other gas giants. It looked like a serene, placid, almost boring planet.
But this calm exterior hides a deeply strange and bizarre reality. The most famous and unique fact about Uranus, as we know, is its extreme axial tilt. While Earth is tilted on its axis by a gentle 23.5 degrees, Uranus is tilted by a whopping 98 degrees. It is essentially orbiting the Sun on its side, like a rolling barrel. This means its seasons are unlike anything in our solar system. For a quarter of its long 84-year orbit, one pole of the planet is pointed directly at the Sun, experiencing 21 years of continuous daylight. At the same time, the other pole is plunged into a 21-year-long, dark and incredibly cold winter. Then, as the planet continues in its orbit, the situation slowly reverses. It's a world of extreme, decades-long seasons. No one is quite sure why Uranus is so tilted, but the leading theory is a familiar one. A giant impact from an Earth-sized object in the distant past likely knocked it on its side.
Voyager 2's encounter with Uranus also gave us our first detailed look at its faint and mysterious ring system. Before Voyager, we knew Uranus had rings because they had been detected from Earth when they briefly blocked the light of a distant star. But we had no idea what they looked like. Voyager's images revealed a system of very narrow, very dark, and very distinct rings. Unlike Saturn's broad, bright, icy rings, the rings of Uranus are made of incredibly dark material, as black as charcoal, and they are surprisingly thin, some of them only a few kilometers wide. The reason they are so narrow and well-defined is thought to be because of small shepherd moons, much like the ones at Saturn, that orbit on either side of the rings, their gravity keeping the dark particles in line. The probe also discovered 11 new small moons orbiting Uranus, adding to the 5 that were already known. And it gave us our first measurements of the planet's bizarre magnetic field. Just like the planet itself, the magnetic field is highly tilted. But it's not just tilted. It is also significantly offset from the center of the planet. It's a messy, lopsided, and wobbly magnetic field that is unlike any other in our solar system. But the most fascinating part of the Uranus encounter was the close-up look at its 5 major moons. And one of them, the innermost moon, Miranda, turned out to be one of the strangest and most visually spectacular objects we have ever seen. It is a quiet little world that seems to have had a very violent past.
Miranda is a small, icy moon, only about 500 kilometers in diameter. But its surface is one of the most bizarre and chaotic landscapes in the entire solar system. It looks as if it has been smashed to pieces and then haphazardly glued back together by a lazy giant. The surface is a jumble of completely different types of terrain, all pushed up against each other in a series of sharp, unnatural-looking boundaries. There are old, heavily cratered regions right next to young, smooth plains. There are vast, deep canyons, some of them 10 times deeper than the Grand Canyon on Earth. And most strangely of all, there are 3 huge, roughly rectangular or oval-shaped features called coronae. These are vast, grooved structures that look a bit like giant racetracks or plowed fields. One of them has a feature that looks like a giant white chevron, a V-shape etched into the landscape. What could have possibly created such a Frankenstein-like world? The leading theory, when these images first came back, was that Miranda had been, at some point in its distant past, completely shattered by a massive impact with another object. The fragments would have remained in orbit, and then, over time, gravity would have slowly and very messily pulled them back together into a jumbled, chaotic new configuration. A more recent theory suggests that the strange features might not be from an external impact, but from the moon's own internal geology.
The idea is that large upwellings of partially melted buoyant ice from the moon's interior could have pushed up on the surface, creating these massive grooved coronae. Whatever the cause, Miranda is a quiet, beautiful puzzle, a tiny world with a remarkably violent and complex history. After its brief but revealing encounter with the Uranian system, Voyager 2 performed one last, perfect gravity assist. It used Uranus's gravity to fling it on the final leg of its grand tour, a 3.5-year journey to the final, unexplored planet in our solar system.
In August of 1989, 12 long years after it had left Earth, Voyager 2 arrived at the 8th and final planet, the deep blue world of Neptune. This was the last planetary encounter of its historic mission, and it was a spectacular finale. Neptune, unlike the placid-looking Uranus, revealed itself to be a vibrant, dynamic, and stormy world. Its atmosphere was a beautiful, deep azure blue, much richer than the pale cyan of Uranus, and it was racked by powerful storms. The most prominent of these was a massive, swirling, dark blue storm system that was immediately nicknamed the Great Dark Spot. It was a huge anticyclonic storm about the size of the Earth, very similar in nature to Jupiter's Great Red Spot. Voyager 2 watched as this great storm and other smaller scooter storms whipped through the planet's atmosphere at incredible speeds. The probe also clocked the winds on Neptune and found them to be the fastest in the entire solar system. Supersonic jet streams, driven by the planet's small but surprisingly potent internal heat source, raced through its upper atmosphere at speeds of over 2,000 kilometers per hour. Why this planet, so far from the sun's energy, has such incredibly fast winds is another quiet and beautiful puzzle of planetary science. Voyager 2 also discovered Neptune's own faint, dark, and clumpy ring system. Unlike Saturn's uniform rings, Neptune's rings have bright, dense arcs where the material is much thicker. It's thought that the gravitational influence of a nearby moon, Galatea, might be responsible for holding these arcs in place, but the exact mechanism is still a mystery. It was another strange and unexpected discovery at the edge of our solar system. But once again, the greatest revelations of the encounter came from one of the planet's moons. Voyager 2 performed a close flyby of Neptune's largest moon, Triton. And Triton turned out to be one of the most fascinating and geologically active worlds in our solar system. First, there is its orbit. Triton has a retrograde orbit, meaning it orbits Neptune backwards, in the opposite direction to the planet's rotation. This is a dead giveaway that Triton is not a native moon that formed in orbit around Neptune. Instead, it is a captured object. It was likely a dwarf planet, much like Pluto, that once orbited the Sun on its own in the Kuiper Belt. Billions of years ago, it must have wandered too close to Neptune and was snared by its immense gravity. This violent capture event would have been catastrophic for Neptune's original moon system, likely destroying it and flinging its remnants into chaotic orbits. Then there is Triton's surface. It is one of the coldest objects in the solar system, with a surface temperature of a frigid -235 degrees Celsius. At this temperature, nitrogen, which is a gas on Earth, is frozen solid and covers much of the surface like a pinkish-white snow. The surface is also incredibly young and varied. One of the most unique features is its cantaloupe terrain, a vast region of the moon's surface that is dimpled and textured exactly like the skin of a cantaloupe melon. No one is quite sure what created this bizarre landscape. But the most stunning discovery of all was that this frozen world is geologically active. Voyager 2's images captured dark plumes erupting from the moon's south polar region. These were cryovolcanoes, or ice volcanoes. Driven by the faint heat from the sun and the moon's interior,
These geysers were erupting a mixture of nitrogen gas and dark, entrained dust several kilometers up into Triton's incredibly thin nitrogen atmosphere, where the plumes would then be sheared sideways by the high-altitude winds. The discovery of active geysers on this distant frozen world was another stunning revelation, a perfect, final, and deeply weird surprise at the end of the Grand Tour.
With its triumphant flyby of Neptune and Triton, Voyager 2's planetary mission was complete. It had successfully visited all 4 of the outer giant planets, a remarkable feat of engineering, navigation, and endurance. Both Voyager 1 and Voyager 2 were now on escape trajectories from our solar system. Their new, final, and perhaps most profound mission had begun, a quiet, endless journey into the interstellar void. But before they left the neighborhood entirely, the Voyager 1 probe, now far out in the dark, was tasked with one final poignant act of observation. This brings us to a quiet, famous moment in our history, a moment born from the passionate insistence of one of the mission's key figures, Carl Sagan. In February of 1990, when Voyager 1 was about 6 billion kilometers from home, far beyond the orbit of even Pluto, the NASA engineers sent a final command to the spacecraft. They instructed it to turn its camera around and take one last look back at the solar system it was leaving behind. It was a risky maneuver. Pointing the sensitive camera optics so close to the bright, distant sun could have damaged them, but the team succeeded. Voyager 1 took a series of 60 images of our solar system from this incredible, distant vantage point. This mosaic of images became known as the family portrait. Most of the planets were just small, faint points of light, but one image in particular would become one of the most famous and influential photographs ever taken. In this image, the Earth is captured as a single, tiny, almost invisible pixel of light. It is less than a single pixel wide. It appears as a tiny, pale blue mote of dust caught in a scattered ray of sunlight that was reflecting off the spacecraft's own structure. This is the iconic pale blue dot photograph. It is our planet, seen from the outside, a tiny stage in a vast cosmic arena.
The image itself is not a spectacular high-resolution masterpiece. It is grainy, and the Earth is barely visible, but its emotional and philosophical power is immense. It is a profound lesson in perspective. Carl Sagan, who had championed the taking of this picture, later wrote a beautiful and moving reflection on its meaning, and his quiet, thoughtful words are worth contemplating. He wrote, "Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam." His reflection continues, noting that our planet is a very small stage in a vast cosmic arena, and that all the great historical conflicts and triumphs have been fought over a fraction of this tiny pixel. He saw the image as a powerful lesson in humility, a reminder of our responsibility to deal more kindly with one another, and to preserve and cherish the pale blue dot, the only home we've ever known. This final poignant photograph was the last picture the Voyagers would ever take. Shortly after, the cameras on both spacecraft were powered down forever to save precious energy for the long interstellar journey ahead. The probes would now be explorers of a different kind, using their other instruments to taste and feel the quiet, invisible environment of deep space. Their mission of seeing was over. Their mission of listening had just begun.
For the next 2 decades, the 2 Voyager probes continued their quiet journey outwards, flying through the vast outer reaches of our solar system's magnetic bubble, the heliosphere. Their instruments continued to measure the properties of the solar wind and the magnetic fields at the very edge of the sun's influence. And they were heading for a boundary that no spacecraft had ever reached before. The heliosphere, as we know, is not infinite. At some point, very far from the sun, the outward push of the solar wind must finally falter as it meets the inward pressure of the interstellar medium, the thin gas and dust that fills the space between the stars. The Voyager probes were destined to be the first human-made objects to cross this final frontier. The first major boundary they encountered was the termination shock. This is the point where the solar wind, which has been expanding outwards at supersonic speeds for billions of kilometers, suddenly and dramatically slows down to subsonic speeds as it begins to interact with the interstellar medium. It is a colossal, invisible shockwave at the edge of our solar system. In December of 2004, Voyager 1, then about 14 billion kilometers from home, officially crossed this boundary. The instruments on board detected the sudden slowing of the solar wind and a jump in the magnetic field strength, confirming they had passed through the shock. After crossing the termination shock, Voyager 1 entered a strange, new, and completely unexplored region of space. This is the heliosheath. This is the turbulent, frothy outer layer of our heliosphere. It's the region where the slowed-down, hot solar wind is deflected and flows along the boundary with interstellar space, much like the water of a river flows around a large boulder at its mouth. This region is a chaotic, messy, and turbulent place. The magnetic field from our sun becomes tangled and foamy. Voyager 1 spent nearly 8 years traveling through this strange, frothy boundary layer, a kind of cosmic purgatory between our solar system and the galaxy beyond.
And then, in August of 2012, something truly remarkable happened. The spacecraft's instruments detected a sudden, dramatic, and permanent change in its environment. The level of high-energy galactic cosmic rays, the particles from outside our solar system, suddenly jumped up by a huge factor. At the exact same time, the level of lower energy particles from within our solar system dropped to almost zero. The data was clear and unambiguous. After a 35-year journey from Earth, Voyager 1 had finally punched through the heliopause. It had officially crossed the boundary and entered interstellar space. It was a monumental achievement, a quiet, historic moment that happened billions of kilometers from home. It was the first time any object made by humanity had ever left the cocoon of our solar system and entered the great cosmic ocean between the stars. This historic crossing was later confirmed in a beautiful and unexpected way. A large solar flare from our sun, back in 2012, sent a wave of plasma traveling out through the solar system. When this wave eventually reached Voyager 1's location, many months later in 2013, it caused the interstellar gas around the probe to vibrate or ring like a bell. This brings us back to one of the most beautiful and strange discoveries of the entire mission: the sound of interstellar space. Voyager's plasma wave instrument was able to detect the vibrations of this interstellar gas. The frequency of these vibrations is a direct measure of the density of the plasma. And scientists found that the plasma around Voyager 1 was about 40 times denser
than the plasma inside the heliosheath. This confirmed without a doubt that Voyager 1 was truly in a new environment. It was in the space between the stars. And by converting these plasma wave frequencies into an audio signal, we were able to hear the sound of the interstellar medium for the first time. A quiet, gentle, and slightly eerie rising tone, the sound of the galactic wind.
A few years after Voyager 1's historic crossing, in November of 2018, its twin, Voyager 2, also crossed the heliopause and entered interstellar space. Because Voyager 2 was on a different, slower trajectory and was heading in a different direction, it crossed the boundary at a different location, and its instruments, particularly its plasma wave instrument, which was still working, unlike Voyager 1's, were able to give us an even clearer picture of this final frontier. The data from both probes has allowed us to start building a map of our own home in the galaxy. It seems our heliosphere, our protective solar bubble, is not a perfect sphere. It is likely a bit squashed and asymmetrical, its shape defined by its journey through the local interstellar magnetic field, much like the bow wave of a ship moving through water. These two tiny ancient probes, built with the technology of the 1970s, are now our only direct observers of the environment beyond our home. They are our silent sentinels in the interstellar void, still, after all these years, patiently sending back quiet whispers about the nature of the great cosmic ocean in which our small, sunny island is floating. And this brings us to the final chapter of their long lives. What does the future hold for these golden wanderers? Their journey through the galaxy will be a quiet and almost eternal one. But their ability to talk to us is not. The radioisotope thermoelectric generators, their nuclear batteries, are slowly decaying. Every year, their power output drops by a tiny amount. To conserve this precious dwindling power, the engineers on the ground have been slowly and methodically shutting down the probe's instruments one by one. The heaters for the cameras, the spectrometers, many of the particle detectors, all have gone silent.
As of today, only a handful of the original scientific instruments on each Voyager probe are still operating. The engineers on the ground have had to make difficult choices, shutting down non-essential systems one by one to conserve the dwindling power from the radioisotope thermoelectric generators. On Voyager 1, for example, the primary instrument still sending back valuable data is the cosmic ray subsystem, which directly measures the high-energy particles of the interstellar medium. The plasma wave subsystem, the instrument that heard the sound of interstellar space, is also still active, listening for any new vibrations in the thin gas between the stars. The magnetometer is also still running, measuring the strength and direction of the galactic magnetic field. Voyager 2 actually has one more instrument still running than its twin. Its plasma science instrument is still functional, giving us direct measurements of the properties of the interstellar plasma itself. This is why Voyager 2's crossing of the heliopause was, in some ways, even more scientifically rich than Voyager 1's. It was able to directly feel the change in the environment, not just observe its effects. But the power continues to drop. Every year, the team on the ground has to make difficult decisions about what to shut down next. Eventually, they will have to start turning off the instruments themselves, leaving only the essential systems needed for communication running. It is a slow, carefully managed, and slightly sad process of putting an old, faithful explorer into its final retirement. The goal is to keep at least one scientific instrument running for as long as possible, to extend this historic mission to its absolute limit. But the day is coming, likely in the next few years, when the final whisper from the Voyagers will be sent, and they will go completely silent forever.
The final shutdown of the Voyager probes will be a quiet, poignant moment. There will be no explosion, no dramatic failure. It will simply be a matter of physics. Sometime around the year 2025, or perhaps a few years after if they can stretch the power, the energy output from the decaying plutonium in the RTGs will finally drop below the minimum level required to operate even a single instrument and the craft's basic communication systems. The engineers on the ground will likely send one final command to the probes, a command to shut down the last of their scientific instruments and their radio transmitter, a final, quiet goodnight. Or perhaps they will simply let the probes drift on, waiting for the moment when the voltage drops too low and their electronic brains simply, quietly, go to sleep on their own. After that moment, the connection will be broken forever. The faint carrier signal that we have been patiently listening to for over a half-century will be gone. There will be only the natural static of the cosmos. The two probes, our farthest and fastest emissaries, will become silent ghosts, drifting ever onward into the vast, dark wilderness of the Milky Way galaxy. Their mission of science will be over, but their new mission, their mission as time capsules, as our silent ambassadors to eternity, will have only just begun. They will continue to travel through the galaxy for millions, even billions of years, long after their creators, and perhaps even the Earth itself, are gone. They will be quiet, enduring testaments to the fact that, for a brief moment in time, a curious species on a small blue planet dared to reach for the stars.
So where are they going? Their future journey is a story of almost unimaginable timescales and distances. They are traveling fast by our standards, but the galaxy is immense. They are not aimed at any particular star. They are just drifting through the local stellar neighborhood. Voyager 1, which is heading in the direction of the constellation Ophiuchus, will have its next close-ish encounter with another star in about 40,000 years. It will pass within about 1.6 light-years of a small, dim star called Gliese 445. From that star system, if anyone were there to see it, Voyager 1 would be a completely invisible, silent piece of ancient alien technology drifting by. Voyager 2, which is heading in the direction of the constellation Sagittarius, will have a similar close pass in about 40,000 years as well, passing about 1.7 light-years from a star called Ross 248. And their journey will continue. They will orbit the center of the Milky Way galaxy, just as our Sun does. They will complete one full orbit of the galaxy in about 225 million years. They will likely survive for billions of years, orbiting the galaxy dozens of times. They might, eventually, be captured by another star system, or have a close encounter that flings them out of the galaxy entirely, into the great void between the galaxies. Or perhaps one day, in the impossibly distant future, they will be found. This brings us back to the Golden Record. Its journey is the true, final mission of the Voyager probes. It is a quiet, hopeful, and deeply philosophical message. Let's take one last, deeper look at the incredible artifact that these probes are carrying into eternity.
Let's revisit the pulsar map, the ingenious diagram etched onto the cover of the Golden Record, designed to be our cosmic address. It is a beautiful piece of scientific art. The diagram consists of 14 lines radiating out from a central point, which represents our Sun. Each of these lines points in the direction of a known, stable millisecond pulsar. And along each line, there is a binary code sequence. This code represents the unique pulse period, the heartbeat, of that specific pulsar. The idea is that an advanced civilization would have their own maps of the galaxy's pulsars. By matching the directions and the pulse periods on the diagram to their own maps, they could triangulate the position of the signal's origin, our Sun. And because pulsars are very long-lived, this map will remain accurate for hundreds of millions of years. But there's another, more subtle layer to it. The binary code for the pulse periods
is given relative to a fundamental unit of time that is also etched on the cover, the transition time of the hydrogen atom. By providing this universal constant, the map becomes a quiet, self-contained scientific lesson. It not only says, "Here is where we are," but it also says, "This is our understanding of physics." There was, of course, a quiet debate among the scientists on the committee about whether including such a detailed map was a good idea. If we don't know if the other hunters in the dark forest are friendly, is it wise to send out a detailed map directly to our home? In the end, the committee's profound sense of optimism won out. They decided that the infinitesimal chance of contact with another civilization and the immense value of representing humanity's hope and curiosity was worth the equally infinitesimal risk. It was a bet on the kindness of the cosmos.
Let's also spend a quiet moment with the images on the record. The selection of 115 images was a monumental task, an attempt to create a visual summary of an entire world. The sequence begins with science. It shows our solar system, our sun, our planets. It has diagrams of our DNA, our anatomy, and our reproduction. It shows a picture of cell division, a quiet testament to the biological engine that drives all life on our planet. Then, it moves on to show the human experience. There is a beautiful and simple image of a man and a woman, with the man's hand resting gently on the pregnant belly of the woman. There are pictures of people from all over the world, a group of school children of different ethnicities, all smiling, a mountain climber on a high peak, Olympic sprinters at the start of a race, a dancer from Bali, a group of artisans from Guatemala. The images were chosen to show our diversity, our art, our work, and our play. There are also images of our world itself, pictures of the Great Wall of China, the Sydney Opera House, and the Taj Mahal. There are images of forests, deserts, islands, and rivers. And there are images of our technology, a picture of a train, a car, an airplane, and of course, a picture of the launch of the very rocket that carried the record. And mixed in with all of this is a quiet, funny little detail. The committee had to get permission to use all of these photographs, but for one of the images, a picture of a busy grocery store, they couldn't identify the photographer. So, they couldn't get official permission. In the end, they decided to include it anyway. They reasoned that if any copyright lawyers wanted to file a complaint, they would have to do so on a world orbiting another star billions of years from now. It's a quiet, humorous footnote in this grand cosmic message.
And so our long, quiet, and very detailed journey alongside the Voyager probes comes to its gentle end. We have traveled with them from their conception as a once-in-a-lifetime grand tour through the brilliant engineering of their 1970s-era technology, and we have admired the profound, hopeful beauty of the golden record they carry as their silent passenger. We have flown with them through the solar system, witnessing their incredible string of discoveries. We saw the raging planet-sized storms of Jupiter and the stunning revelation of active volcanoes on its moon, Io. We marveled at the intricate, braided, and impossibly thin rings of Saturn, and we got our first hazy glimpse of the strange orange world of Titan. We made the lonely journey with Voyager 2 to the outer ice giants, seeing the placid blue face of Uranus and its bizarre Frankenstein-like moon, Miranda. And we finished the planetary tour at the deep blue, windy world of Neptune, with its own ghostly rings and its strange captured moon, Triton, with its geysers of nitrogen frost. And then we journeyed with them onwards into the great, dark unknown. We looked back with them to see our entire world as a single pale blue dot, a quiet, humbling lesson in cosmic perspective. And finally, we crossed the final boundary, the heliopause, and became the first emissaries of Earth to enter the true, silent space between the stars. We have even listened to the quiet, ethereal sound of the interstellar wind that they are now sailing on. What, then, is the final, quiet legacy of these two incredible machines? It is a story of pure exploration. The Voyager missions were not about finding resources or claiming territory or looking for life. They were born from a simple, powerful, and deeply human desire to see what was out there. They were an act of pure curiosity, a journey to the outer planets simply because they were there, and we had, for the first time, the ability to go.
The scientific return from the Voyager missions is almost impossible to overstate. They completely rewrote our textbooks about the outer solar system. Before Voyager, we thought the moons of the outer planets would be dead, cratered ice balls. But Voyager showed us that they are some of the most dynamic, diverse, and geologically active worlds in our entire solar system. The discovery of Io's volcanoes and the strong evidence for Europa's hidden ocean were two of the most important discoveries in modern planetary science, and they have completely changed the way we think about where the search for habitable environments. The Voyager probes were a triumph of engineering. These machines, built with less computing power than a modern digital watch, have survived for nearly half a century in one of the most hostile environments imaginable. They have endured the intense radiation belts of Jupiter, the bitter cold of deep space, and the constant, quiet bombardment of interstellar cosmic rays. Their longevity is a quiet testament to the skill, the care, and the slightly paranoid, redundancy-focused philosophy of the brilliant engineers who built them in the 1970s. But perhaps the most profound legacy of the Voyager probes is a philosophical one. They are a story about time. The light from the stars takes years to reach us, but these probes are traveling so slowly that their journey to the nearest stars will take tens of thousands of years, and their journey through the galaxy will last for billions of years. They are our silent, immortal ambassadors. They will likely outlive not just every human being who is alive today, but perhaps our entire species, and maybe even the Earth itself. When our sun swells into a red giant 5 billion years from now and consumes our planet, the two Voyager probes, with their golden records, will still be drifting silently through the Milky Way, carrying a quiet, final memory of our world, our music, and our hope.
And that brings us back to the golden record. It is, I think, the most hopeful and most poignant part of the entire Voyager story. It is a symbol of our better nature. It represents a moment in our history when, in the midst of a tense Cold War, we decided to send a message of peace and friendship out into the cosmos. The record doesn't just contain the achievements of one country. It contains the music and the languages of the entire world. It is a message from a unified planet. And the message itself is one of profound optimism. The very act of sending it is an act of hope. It is the hope that there might be someone else out there to receive it. It is the hope that we as a species will survive long enough to one day join a community of galactic civilizations, as President Carter's message said. And it is the hope that we will be remembered not for our conflicts, but for our curiosity, our art, and our desire to reach out and say hello. The chance of the record ever being found is, of course, infinitesimally small.
The probes are tiny, and the galaxy is vast. But that doesn't matter. The importance of the golden record is not in its reception, but in its creation. It was an act of looking at ourselves, of trying to decide what parts of our humanity were most worth preserving and sharing. It was a mirror that we held up to ourselves and then sent out into the universe. So as you get ready to drift off to sleep tonight, let the quiet story of these two golden wanderers be a comforting presence. Think of them right now, drifting silently through the cold, dark space between the stars, farther from home than anything we have ever made. They are carrying their golden records, their quiet symphony of earthly sounds and sights, on an endless journey.
Think of the incredible journey they have taken, from the fiery launch pad in Florida, past the volcanoes of Io, through the magnificent rings of Saturn, past the tilted, ghostly Uranus, and by the cryovolcanoes of Triton. Think of the patient, dedicated team of scientists and engineers on the ground who have been listening to their faint whispers for almost 50 years, a quiet, multi-generational conversation across billions of kilometers. And think of that final, poignant look back at the pale blue dot. Think of our entire, noisy, complicated, beautiful world, with all its history and all its future, reduced to a single, tiny, fragile pixel suspended in a sunbeam. It is a quiet, powerful reminder of our true place in the cosmos. It's a perspective that can make our own earthly worries and anxieties feel very small and very distant. The story of Voyager is a story of pure exploration at its finest. It wasn't about commerce or conquest or national security. It was about knowledge. It was about wonder. It was about the simple, powerful human need to see what is over the next hill, even when that hill is on another planet in another part of the solar system. It is a quiet, hopeful, and deeply inspiring story. It's a testament to our ingenuity, our curiosity, and our ability to dream on a cosmic scale. The two Voyager probes are perhaps the greatest legacy of our species so far. They are our quietest and our longest story, a tale that will be told in the language of physics and orbital mechanics for billions of years to come.
So let your mind be at ease tonight. The universe is a vast and ancient place, and we are just beginning to explore it. There are still so many quiet mysteries to ponder, so many new worlds to discover. The story of our exploration is still in its very first chapter. But we have sent our messengers ahead of us, two small, quiet ambassadors from a world of oceans and music and laughter. They are carrying our story into the great silent night, and in that thought, in that quiet act of hopeful communication, there is a deep and profound peace. Let that peace be with you now as you drift off into your own quiet journey into the world of dreams.